chapter 10, number 66. It's actually a little complicated trying to understand what the problem is asking. But, you should really read what the problem is asking and then compare that to what I have up here. Because it talks about a thin rod suspended freely from one end. So notice that this is suspended freely from one end. And it's pulled to the side an angle of theta. We don't know how big that angle is. It could be 90 degrees, it might not be. And we need to find the angular speed of the rod as it reaches the bottom part. Because it's going to keep swinging, but we're just looking at when it reaches them. And then what's the speed of the very tip of the rod at the bottom. So, first of all, there are a lot of things to work with here. One is that the kinetic energy, when we're talking about rotation, is not 1/2 mv squared. It's a rotational version of m, which is the moment of inertia, and the rotational version of velocity, which is omega squared. 1/2 mv squared f I w squared. Okay. Also good to know that for a rod that rotating by its end is 1/3 mr squared. Now, the formula for this would we use a conservation of energy. Energy before plus the kinetic energy before, but in this case it's purely rotational, equals potential energy after plus energy after. Now it has potential energy here, but no kinetic rotational energy just yet. And at the bottom, its potential energy has gone to 0, but it has rotational energy. So, this is mgh plus 0 equals 0 plus 1/2 I omega squared. The height. What is the height? Well, whenever we look at the change in height, we're always doing it from the center of mass. Center of mass. So it doesn't look changes all that much, right? From here to here down below. Okay. So, in order to find this, we do what we did before with the pendulum. This length here is, if the whole length is L, the length is half of that. You divide L by 2 to find half its length. So, if it started out here, we want to look at this triangle here. This is theta. We want this distance If we know this distance, then we know what to subtract from L over 2. So here's a triangle. It's a right triangle. Here's theta. So that part there is L over 2 cosine theta. I know this is related to C, but essentially what we're doing is we're taking the side. That's not straight down. So that's L over 2. Or subtract this amount, L over 2 cosine theta. And by subtracting this, we'll get this piece. And that's the distance the center of mass falls. So that's L over 2 minus L over 2 cosine theta. So the height, L over 2 minus L over cosine theta. We got L over 2 cosine theta from the angle that we made. The center of mass started there. So doing a horizontal line across its height. This is what we found. Okay. Simplify this. The height is the same as L over times 1 minus cosine theta. Now we're losing the meaning of the math. I understand that. Here it was meaningful. It was saying the entire length minus a certain part of the length is how much height it dropped. Here we found, and now it's kind of lost its meaning. But it's easier to plug in the number. You don't have to plug in L twice, even though there is no numbers. There are no numbers. Okay, so we put that in. We get L over 2 cosine theta. Okay. Equals 1/2, and I is 1/3 mr squared omega squared, and the s divide out. We'll continue in just a minute.